Okay, morning class, right? So today we continue our discussion for paper one. Okay. Before that, I already got a few trial paper from another state. Okay, for this year. Okay, so maybe I will divide the trial paper right, according to the chapter first, okay, then I will give it to you. Okay, so in case the MCO still continues, right, I will give it in the group, okay, in the GC. Okay, if not, if the school open, okay, so maybe I will give you the hard copy. If not, maybe just soft copy. Okay, then we discuss lah. Okay, for this year trial from another trial paper from another state. Okay. So continue our discussion, right? So this is the number 73. Okay. So diagram below shows the water is flowing, okay, entropy and flowing up from Q. Okay, so this will affect the level of water in each tube. Okay, so which of these tubes, okay, will experience the highest pressure? So this one is actually a Bernoulli, right? So here, okay, so the velocity is high, right? So means the pressure is low, okay? So when the pressure is low, means the water cannot rise, okay, too high. So it should be here. So, okay, and then this one, the velocity is low, means the pressure is high, right? So the water will rise up, okay? Right, and then this one, the velocity is still low, okay? Okay, compared to this one, but the pressure will be very high, okay? So here, okay, and then this one because this one is high, okay? So velocity is high, okay, and then the pressure is low, okay? So means it will be like here, okay? Same as this one. Okay, so for this one, ask you to find the tube that has the highest pressure. So highest pressure is tube 3. Okay, so the answer is C. Okay, alright, then move on to the next question. Okay, diagram below shows a Bernoulli tube. Okay, air is blown from right to left. Okay, so which of the following diagram shows the correct level of water in tube P, Q, R, and S? Okay, so for this one, this is also Bernoulli. Okay, so velocity is low. Okay, so pressure is high. Okay, so means when the pressure here is high, the water cannot rise up. Okay, because this one the pressure is high, it will push down the water. Okay, so the water should be the lowest here. Okay, and then for this one, the velocity is high. Okay, so pressure is low. Okay, for the second tube. So when the pressure is low, okay, means the water can rise up. Okay, because the pressure is low, so it cannot push down the water. Okay, the water downwards. Means it will be uh rise up, okay, like this. Okay, and then for this one, the velocity is very high compared to tube 2. Okay, so means the velocity is very high, the pressure will be very lower here. Okay, so when lower means the water rise up more like this. Okay, and this one because because the air is just come from the higher velocity place. Okay, so means this one the velocity is higher that to compare to this one, the first tube. Okay, so means the velocity one is the lowest, and this one is only lower, so the pressure is higher, so it will be on the middle. Okay, this. Okay, so the answer should be P is the lowest. Okay, P is the lowest. Q, R. Okay, so the answer should be C. Okay, so the answer should be C. Alright, the next one question. Okay, so this is the Archimedes, right? So if the weight of the boy and the raft is 1,200, okay, what is the volume of the water of the raft, okay, which is submerged, okay? So this one we know because it's floating, right? So means the weight is equals to the buoyant force, okay? The weight of the object is equals to the buoyant force. Okay, so means mg is equals to rho v g. Okay, because the object is floating, right? Okay, so the weight is already given, right? 1,200. Okay, and then the density is 1,000. Okay, v you need to find, and g is 10. Okay, so you find the value of v. So v is actually 0.12. So the answer is A. Okay, so the answer is A. Right? So you have to remember when the object is floating, okay, floating stationary, the weight is actually equals to the buoyant force. Okay, so you can use this equation. Alright, next one. Okay, so we go to the gas law, right? So we go to the gas law. So in chapter 4, okay, so chapter 4, we already learned about heat, right? So heat, the first topic is specific, no, thermal equilibrium, and then second one is the specific heat capacity, third one is the specific latent heat, and last one is the gas law, okay? So gas law is actually got three gas law, okay? The first one is a Boyle's law, okay? So Boyle's law said the pressure is inversely proportional to its volume. So means if the pressure is increased for the gas, the volume will be decreased, okay? So this is the relationship, okay, and then this one is the equation. Okay, P1 V1 is equals to P2 V2. Okay, so how about the graph? Okay, so since P is inversely proportional to V, okay, so this the graph will be like this. Okay, it will decreasing like this. Okay, but let's say if the graph is P against 1 over V, okay, so it will be directly proportional. Okay, if the graph is PV against V, okay, it will be like this, stationary like this. Okay, and PV against P also, okay, the graph should be stationary like this. Okay, so this is the graph of Boyle's law, right? So second one is the Pressure's law. Okay, so Pressure's law state, okay, the pressure of gas is directly proportional to its absolute temperature, okay, when its volume is constant. So P is directly proportional to T, okay, and if you use the formula, okay, if you want to calculate to use the Pressure's formula, the T must be in Kelvin, okay. So let's say it's in degrees Celsius, okay. So you have to change to Kelvin first. So how you want to change to Kelvin? You just add 273. So please don't forget, okay. So if you want to use the gas law, the temperature must be in Kelvin. So you have to convert it first, okay. Alright, and then the graph, okay, so the graph, if the graph, the x-axis in degrees Celsius, okay, so the graph is actually increasing linearly, okay, it will not pass through the origin, okay, but if you extrapolate the graph, okay, and make it longer, and it will reach until the x-axis here, okay, it will intercept at x-axis there, so this one is called as a absolute temperature. Okay, absolute temperature. So what does it mean by absolute temperature? Is where the molecule, the kinetic energy of the molecule is almost zero. Means the molecule is not moving, right? But if the graph, okay, the x-axis in Kelvin, okay, so the graph is pass through the original. Okay, it will pass through the origin. Okay, origin here. Okay, so you have to differentiate. Okay, we see the axis first. X-axis whether degree Celsius or Kelvin. Okay, so this is the Pressure's law. Okay, all right. The next one is Charles law. Okay, so Charles law said the volume is directly proportional to its absolute temperature. Okay, when the pressure is constant, right? So same V1 divided by T1 is equals to V2 divided by T2. Okay, for Charles' law, it's same like the previous law. Okay, the graph is increasing linearly. Okay, but if you make it longer, okay, you will intercept at x-axis. Okay, so the value should be negative 273 degrees Celsius. Okay, and then this one is also called as the absolute temperature. Okay, if the x-axis is degrees Celsius, it is increasing linearly. If the x-axis is in Kelvin, it will directly proportional. Okay, so this is for the Charles law. Okay, and then the next one is the absolute temperature. Okay, so absolute temperature is measured in Kelvin. Okay, if you convert degrees Celsius to Kelvin, okay, you have to add 273. Okay, if the Kelvin change to degrees Celsius, you have to minus 273. So absolute zero is the lowest possible temperature, okay, which is negative 273. Okay, and this one at this time the kinetic energy is molecule of kinetic energy of the molecule is zero. Okay, almost zero. Okay, so let's see the question. Okay, chapter 4, right? So is this one is table 1 shows the volume and the temperature of a certain mass of gas kept at a constant pressure. Okay, so this one is actually Charles law, right? Okay, so V1 T1 goes to V2 T2. Okay, remember this one you have to change to Kelvin. So 50, okay, so this one change to Kelvin 273 plus 30, okay, equals to V2 is 100, okay, divide by T2, okay, and then you cross multiply, okay, cross multiply, and then after you got the answer, okay, you have to minus with 273 because the answer is in degree Celsius, right? And this one if you use a Kelvin, right? So change back to degree Celsius, so minus 273, so you got the answer is B boy. Okay, right, next slide. Okay, specific heat capacity. Okay, so what is the specific heat capacity? Okay, so specific heat capacity is the quantity of heat energy to raise the temperature of 1 kg of the substance by 1 degree Celsius. Okay, right. So if the question just asks you the definition of the heat capacity. Okay, so heat capacity means you don't no need to put 1 kg here. Okay, so mean only quantity of heat energy required to raise temperature, okay, of 1 degree Celsius, okay, without the kg, right? And then the unit for the specific heat capacity is JkG negative 1 degree Celsius negative 1, okay? So low specific heat capacity and high specific heat capacity. So how you want to differentiate between these two? Okay, usually the low specific heat capacity, okay, the object is easy to be hot, right? And then the high specific capacity, okay, usually the object is take time to heat up, okay. So that's the difference, okay, between the low specific heat capacity and also the high specific capacity, okay. And for if you want to compare, okay, low specific capacity and also the high specific heat capacity, okay, the object will cool faster, okay, for the low specific heat capacity, right? Okay, so how you want to calculate, right, the quantity of heat, okay, the quantity of heat. So usually we use a formula. Q is equals to MC theta. Okay, so this is actually the formula for quantity of heat, right? But let's say if the formula give you a power, okay, a power of the electrical energy, okay, the power of the electrical appliance, okay, let's say they use the emission heater, okay, so then they give you the power. So how you want to use the formula for if they give you the power, you can use this one. Okay, PT is actually equals to MC theta. So what is actually PT? Okay. So let's say if I have a beaker, okay, and then I use the emission meter here, okay, and then I heat up, okay, connected it to the power supply. Like this is the experiment for the trial, right? Trial exam, right? Okay. So let's say the power here, the power of the emission is 50 watt, right? Okay. So what is the PT actually? Okay. So before you heat up the water, okay, before you heat up the water, so the first energy, okay, the first energy that we get is actually from the electrical energy. Okay. So PT is actually the formula for electrical energy. Okay, and then MC theta is a formula of quantity of heat energy, right? So mean we use the principle of conservation of energy. We assume that, okay, we assume that the energy that is supplied by the electrical here, okay, by energy that is supplied by the power supply here is actually is equals to the energy, heat energy here that is supplied to the water. Okay, so means we use the principal conservation of energy. So energy is not lost to the surrounding. Okay, it will be conserved. Okay, so this is how the formula come out. Okay, we assume that the electrical energy is equals to the heat energy. So where's the electrical energy come from? It's actually come from the power supply. So we use the energy that's supplied by the power supply. Is we assume that is same as the heat energy that we get to the water, right? Okay, so this is the formula. Alright, then next one. Okay, okay, next is a specific latent heat. Okay, so specific latent heat is the energy absorbed or released, okay, when a substance change its physical state completely at the constant temperature. Okay, so let's say from solid to liquid. Okay, so this the process is known as melting, right? Okay, so when solid change to liquid and it does not increase, the temperature is not increased. Okay, so the energy that been used, okay, to transfer from solid to liquid, okay, that one we call it as a specific latent heat. Okay, without increasing the temperature. Okay, or from liquid to solid. Okay, so that one is also called as a latent heat of fusion. Okay, and then liquid to gas. Okay, so liquid to gas, the temperature is not increased, but only the state of the physical state of the substance only change. Okay, like liquid to solid, solid to liquid, liquid to gas, right? So for this one, liquid to gas. Okay, so it changed state. Okay, but the temperature is not increased. So this one we call it as a specific latent heat. Okay, or maybe you can understand it more if we use a graph. Okay, okay, heating. Right. So this is the temperature and this is the time. Okay. So this one is solid. This one is solid and liquid. Okay, and liquid. This one is liquid. This one is liquid and gas. Okay, and then this one is gas. Okay, so let's say for this. Okay, okay, so this at this part, okay, at this part, okay, you can see the temperature is not changed. Okay, so and but the substance is changed from solid to liquid. So at this part is actually for the specific latent heat. Okay, and how about this one? Okay, this one the temperature is changed. Okay, the temperature is changed. So this one is actually specific latent heat. Okay, and for this part we call it as the latent heat of fusion, right? That means solid change to liquid. Okay, and then for this part you can see the temperature increasing. So this one is specific heat capacity. Okay, and for this one liquid and change to gas. Okay, and you can see the temperature is not changed. Okay, it's constant, right? So means this one is specific latent heat, but latent heat of vaporization. Okay, and if the question asks you, okay, why the temperature is not increasing even you still give the heat to the substance. Okay, so this one is actually to overcome, okay, to overcome the attraction, okay, between the molecule. Okay, so that's the answer. Okay, so this is specific latent heat. Okay, and the unit for the specific latent heat is joule. Okay, and process in which solid directly change to vapor is called as a sublimation. Okay, so the sublimation. Okay, this one is the graph, okay, that I already explained. Okay, so this one is solid, solid plus liquid, liquid, liquid plus gas. This one is gas. So this part latent heat of fusion, and this part is latent heat of vaporization. Okay, so we try to answer this question. Right, number 23. Okay, hot water at 100 degrees Celsius. 100 degrees Celsius. Wait, I find the question. Okay. Hot water at 100 degrees Celsius is added to 5 grams of ice, okay, at 0 degrees Celsius. So what is the minimum mass of hot water needed to melt the ice? Okay, for this one, we assume that the quantity heat energy for specific heat capacity is actually same as the quantity heat for the specific latent heat. Okay, so means mc theta is equals to ml. Okay, so the mass here, okay, you need to find the m. Okay, and then the c is given specific capacity 4.2. Okay, 4.2. Okay, and then multiply by theta is 100 because it said 100 to 0, right? So change of the temperature. So 100, okay, equals to, so the mass here is, the m here is 5, I think. Wait. No, this one is 5. Wait, I calculate it wrongly here. MC theta is equals to ml, right? So what is the minimum mass hot water needed to melt the ice? So ice is 5 here. Hot water C is, oh, sorry. MC theta is equals to ml. So hot water is added to 5 grams of ice at 0. What is the minimum mass of hot water needed to melt the ice? So ice is will be melt is m here. L is 336. Okay, and this one mass you need to find. Okay, so C is 4.2. Okay, theta is 100. Okay, and then you try to calculate. Okay, 5 times 336 divided by 4 times. The answer is B boy. Okay, so the answer is B boy. Okay, MC theta equals to ml. So M you need to find the mass of hot water. C is 4.2. Theta is the change of temperature. So 100 minus 0. Okay, and then M is the mass of the ice. So 5. Okay, 336 is the specific latent heat of the ice. Okay, to change it to water, right? Okay, so the answer is 4. Alright, so we move on to the next question. Okay, as an experiment is carried out to investigate the change of pressure with temperature for a fixed mass of gas in the conical flask. Okay, so this one is pressure against temperature. So this one is actually Pressure's law. Okay, so you can see the x-axis in degrees Celsius. Okay, so should be the graph is increasing linearly. So number 23, the answer is D donkey. Okay, D donkey. Alright, next one. Okay, so an enclosed container contains a fixed mass of gas at 27 degree and atmospheric pressure. Okay, the container is heated and the temperature of the gas increases to 87 degrees Celsius. Find the new gas pressure if the volume of the container is constant. So means you have to use what gas law is this one? This one is temperature and also pressure, right? So temperature and pressure, so means P1 over T1 is equals to P2 over T2. So this one is a pressure's law. Okay, so P1 is atmospheric pressure. Okay, because it say atmospheric pressure. So this one when 1 times 10 power of 5. So you just substitute 1 times 10 power of 5. Okay, and then the T1 you have to change to Kelvin. So 273 plus 27 is 300. Okay, and P2 you need to find. Okay, okay, and then the temperature here, the new temperature here is 87. So you just add 273 plus 87, you get 360. Okay, and then you cross multiply. So you got P2 is B bomb. Okay, so it is the precious law. Okay, next one. Okay, so this one diagram below shows a temperature against time graph for 600 gram of liquid X that is heated by 100 watt electrical emission heater. So determine the specific capacity of liquid in J kg negative 1 degree Celsius negative 1. Okay, for this one you need to use the formula Q is actually equals to MC theta. Q is equals to MC theta. Alright, but you know it doesn't give you the quantity of heat energy here, right? So what you should do, you can use because it gives you the power here, okay? Okay, so you can use PT is equals to MC theta. Okay, so the power is 100, okay? And the time must be in second. So 6 minutes, so change to second multiply by 70, you got 420. Okay, and then the mass must change to kg. Okay, you have to see the unit here. Okay, so kg 0.6. Okay, and C you need to find. Okay, theta is the increasing. Okay, the increasing temperature. So 30. This one is 60, right? So 60 minus 30, you got 30. Okay, and then you just use the calculator to calculate. So you got the answer is D donkey. Right? D donkey. Okay, next one. Okay. Number 19. Okay, diagram 14 shows the length of the air column trapped at 27 degrees Celsius. So what is the length of the air column at 100 degrees Celsius? So this one is actually gas law, right? So what gas law? So we have to see what is the variables given here. So this one is a temperature, right? And then this one is 10 cm. So actually 10 cm is actually represent the volume. Okay, so volume and temperature, so this one is Charles' law. So V1 T1 is equals to V2 T2. Okay, this one. Alright, so the volume here is 10 cm, right? The temperature here 273 plus 27 should be 300. Okay, and V2 you need to find. Okay, so T2 is 100 degrees Celsius. So 273 plus 100 is 373. And then you just cross multiply. Okay, so you got the answer is C, 12.4. Right? Okay, so next one. Okay, diagram 15 shows a block L and block M of different material are in thermal equilibrium. Okay, so thermal equilibrium means the temperature must be same. Okay, if no temperature, the answer no temperature is same. So you have to find the net rate of heat transfer is 0. Okay, so the answer is C. Or you can find the rate of heat transfer between two objects is same. Okay, that one is also thermal equilibrium. Okay. Okay, an experiment is carried out to investigate the change of volume with temperature for a fixed mass of gas. Okay, so volume and temperature, this one is Charles' law. Okay, so since the x-axis is in degrees Celsius, so it should be increasing linearly. So number 15, the answer is D. Only if the x-axis in Kelvin, then you pass through the origin. Okay, so number 15, the answer is D donkey. Alright, next one. Okay, so this is the gas law, right? So using the gas law, okay, so this one is pressure and temperature. So this is a pressure law, okay? Use pressure's law. So P1 is T1 is equals to P2 over T2. Okay, and then you just substitute, right? 360, okay, 273 is 300. Okay, change to Kelvin. Okay, 2273 plus 27. And this one is T2. You need to find. T2 is 313. And then you just cross multiply. Okay, so you got the answer is C. Okay, number 19, the answer is C. Right. Okay, next one. Okay, which graph shows the relationship between pressure and volume of gas that obeys Boyle's law? Okay, so for the graph of Boyle's law, okay, if P against V, okay, should be inversely proportional. Okay, if P against 1 over V, okay, it should be directly proportionally. If PV against P, okay, the value should be constant like this. If PV against V, okay, is same, should be constant like this. So which one is the correct one? So the answer should be A, right? Okay, next one. Okay, diagram below shows three blocks PQR at temperature T1, T2, and T3 respectively are in contact with each other. So which combination of temperature shows the three blocks above are in thermal equilibrium? So thermal equilibrium, the temperature should be same. So the answer is A. Okay. So number 31, the answer is A. Okay, next one. So 50 gram of water at temperature 0 degrees is mixed with a 50 gram of water at temperature 30 degrees Celsius. So what is the final temperature of the mixture? So this one, okay. So let's say, okay, I have a 2 beaker here, right? Okay, so this one is in 0 degrees Celsius. This one is 30 degrees Celsius. Okay, so when I mix the both of the water here, okay, 0 degrees Celsius and 30 degrees Celsius. So I want to find the final temperature for this both, okay, water after it being mixed. So we assume here, right, the heat absorbed. Okay, the heat absorbed by water is actually the heat absorbed released by the water. Okay, so MC theta is equals to MC theta. Okay, so which one that will absorb and which one will be released? Okay, so this one will absorb because this is the lower temperature, right? So and you know the energy, the heat energy transfer from the hot object to the cold object. So means this one we lost the energy. This one will receive the energy here. Okay, so this one will be absorbed and this one should be released. Okay, so I put here absorb. Okay, so we know the chain here and this one is release. The difference here. Okay, so the absorb is this one. So use the mass here. So 50 divided by 1000, you got 0.05. Okay. And C, we can ignore the value of C. Okay. Why? Because if you change here, C will divide by C also, right? So the same, you will, okay, just cut it off like that. Okay, so theta. So theta, 0 degrees Celsius. So this one, the temperature will rise, right? Because it's absorbed the heat energy. So the temperature will be rise. Okay, so this one should be theta minus 0. Okay, you need to find the theta. Theta minus 0. Okay, but for this one, okay, so the M same 0.05 also, since it's 50 gram. Okay, and C just ignore. Okay, for theta, this one, the 30 degrees, the temperature will go down. Okay, will go down. So means the theta minus, sorry, the 30 minus theta. Okay, 30 minus theta. Okay, the temperature will rise. Okay, will not rise, will decrease. Okay, so 30 minus theta. This one, the temperature will rise up, so will increase, so theta minus 0. Okay, and then you need to expand it. Okay, and then find the value of theta. So the value of theta, okay, so I get the answer is B boy. Okay, so for this one, if the two water that been mixed up and you want to find the final temperature, so you have to assume that heat absorbed by the water and is same as the heat absorbed released by the water. So you have to differentiate between who will absorb and who will release the heat. Okay, so this is the equation. Okay, so we move to the next question. Okay. Okay, for this one, the diagram above shows a gas trapped inside a cylinder. So pressure inside the cylinder is P. The piston is pushed in a distance of 30 cm so that the length of the gas column is now 20 cm. So the pressure of the gas does not change. So this one is pressure and volume. So use Boyle's law. Right, P1 V1 is equals to P2 V2. Okay. So the pressure inside the cylinder is P. So we replace P1 with P. Okay. And V1, the value is, the volume of the gas is 50 here. Okay. And P2 you need to find. Okay. And then it said it push a distance of 30. So now only left 20 cm. So the new volume is 20. Okay. And then you want to find the P2. Okay. So 50P divided by 20. Okay. So P is 2.5. So the answer should be D donkey. Right. The next one. Okay, the diagram shows a metal cylinder of mass 5 kg and the specific heat capacity 400 J/kg, negative 1 degree Celsius, negative 1. So what is the temperature rise of the cylinder 10 seconds after the heater is switched on? Okay, so this one you have to know, you have to use this formula. Q is equals to mc theta. But the formula, but the value of the quantity of heat energy, okay, is not given here. So, and you can see they give you the power here, right? Okay, so use PT is equals to MC theta. Okay, we assume that the energy, the electrical energy supplied to the emission here is actually equals to the heat energy, okay, being absorbed by the water here. Okay, so P is 1000, okay, and time we need to given you 10 seconds, and then the mass is 5. C is 400. Okay, theta you need to find the rise of temperature. Okay, so you've got the answer here. D. Okay, 5 degrees Celsius. Right. So we move on to the next one, next question. Okay. So table shows the specific heat capacity for materials R, S, and T. So which of the following pair is most suitable for making the base and the handle of the frying pan. Okay, so this one, base of the frying pan must be easy to heat up. Okay, the temperature must be easy to rise up. So of course the specific capacity should be lower. So the base must be R, okay, and the handle should be high specific heat capacity. So R and T. So number 18, the answer is A. Okay. Alright, next one. Okay, diagram shows a balloon filled with the cool air is placed in the hot room. Okay, after a while, okay, what happened to the balloon? Okay, so what happened to the balloon? Alright, so here the surrounding is the hot room, meaning the hot air. Okay, the air is hot. So when the air is hot, mean the density is lower, right? The hot air has a low density. Okay, so has a low density. Okay, so you know the formula rho Vg. Okay, so when the density is lower, the buoyant force also should be lower. Okay, and here inside the balloon is a cool air. So cool air means the density is higher compared to the surrounding, right? So when the density is higher means here the mass is bigger, right? Okay, so the weight is bigger than the buoyant force here. So it will fall to the floor. Okay, so the answer should be B boy. Okay. Alright, so next one. Okay, diagram shows a process in which water change to steam. Okay, so the heat absorbed during the process is called as a, okay, if the specific heat capacity, the state of the physical state of the substance will not change. Okay, only for the latent heat that the physical state of the substance will change. So in this one is water to steam, means the physical state of the substance is changing, right? So means this one should be latent heat. Okay, so whether fusion or vaporization, so water to steam, of course, vaporization. So the answer number 20 is C. Okay. Alright, number 28. Okay, so diagram 14 shows the formation of a land breeze. Okay, so it said here, which of the following statement is correct? So the pressure of the sea is higher than the land. Okay, so this one, the pressure of the sea is higher than the land. No. Okay, for B, the density of air above the land is less than that of above sea water. Okay, so this one, the the land has the low specific capacity, right? So let's say if during the daytime, this one will be heat up faster. Okay, so the air is the density of air, okay, at the land is lower when at the daytime. Okay, so number B, the answer is wrong. Okay, the temperature of the land become higher than the temperature of the seawater. This one is only at daytime, okay, not at the night. Okay, so the answer is D. Okay, the specific capacity of seawater is higher than the specific capacity of the land. So the answer should be D. This one is actually for B and C is during the daytime. Okay. Alright, number 19. Okay, number 19, diagram 15A shows an amount of water is heated continuously using an emission meter. So diagram 15B shows the water after being heated for 5 minutes. Okay, so based on diagram and the information given, determine the specific latent heat of vaporization of water. Okay, so this one we use the, okay, PT is equals to ML. Okay, means the heat, okay, the heat energy, sorry, the electrical energy being supplied to the emission heater here is equals to the heat energy for the specific latent heat. Okay, So PTP is 25. Okay. T is 5 minutes, right? So change to seconds, 300. Okay. The mass is 100 minus 97. 3 gram, right? Only 3 gram that changed to vaporization. That changed to water vapor, right? So we use 3 gram only, and the L you need to find. Okay, for this one need to change to kg first. Okay, because the unit is in kg. So 3 divided by 1000. Okay, so you got the value of L is 2.5 times 10 power of 6. The answer is D. Okay, so means the electrical energy, PT here, okay, 25 minus, 25 multiplied by 300 is used to change the 3 gram of water, okay, to the water vapor. Okay, so means the electrical energy here is is used to change the 3 gram of water to water vapor. Okay, so the answer should be D. Alright, next one. Okay, so this one is the gas law. Okay, already said to investigate Precious law. So which graph shows the relationship between the difference in height of water levels H and the absolute temperature T for a fixed mass gas at constant value? Okay, so this one is T against T. Okay, so wait. This one is not Precious law, right? Because there's no Borden gauge, right? This one is actually Charles law. Okay. H is actually represent, oh no, yeah. This one is Precious law, correct. This one is actually to measure the pressure, manometer, right? Okay, so the answer should be H and T. So the answer is D donkey. Right, because this one is in Kelvin. Okay, this one is in Kelvin, so the answer should be D. 20 is D. Alright, 21. Okay, so the spark from the firework, okay, which falls on the boy's hand does not produce severe burns because of the spark has a low specific heat capacity. So the answer 18 is D donkey. Okay, number 18, the answer is D donkey. Alright, for number 19, this one you have to use the formula L theta minus L0, right? Equals to L100 minus L0 multiplied by 100, right? So L theta minus L0 divided by L100 minus L0 multiplied by 100. Okay, so L theta, so read the question first. It said the length of the mercury column is 5 cm at 0 degrees Celsius. So means should be 5 cm is the L0. The length of the mercury when it's 0 degrees Celsius, L0. And 65 at 100 degrees Celsius. So mean L100 is 65. Okay. And then it said when the temperature is placed in the hot water, the length of the mercury column is 40 cm. So what is the temperature of the hot water? So L theta is the length of the mercury that we need to find the temperature. So this should be L theta. Okay. So L theta is 40. Okay. L0 is 5. Okay. L100 is 65. L0 is 5. Okay. And then multiply by 100. Okay. Then you just use the calculator, so you got the answer B boy. Okay. And this one, the formula you need to remember, it's not given. Okay, move on to the next question. So diagram 20 shows a metal cylinder of mass 3 kg and the specific heat capacity 1600 and is heated with the heater of power 2 kilowatt. So what is the rise temperature? This one is same like the question before, right? But this one only the value is changed. Okay, so you just use the formula PT is equals to MC theta, right? So PT 2 kilowatt. So make sure when you if you want to answer the calculation question, you have to make sure the prefix, whether they use the prefix or not. Okay, if they use, you have to change it. Okay, So time here is 1 minute, change to second, 60 second. The mass is 3, C is 1600. Data you need to find. Okay. So the data should be, C. The answer is 25. Okay. So the answer is 25. Okay, so we move on to the next question. Okay, a balloon is put under the sun until the volume is increased. So which of the following is correct about the mass of the air and the kinetic energy? Okay, so the mass of the air is same. Okay, it's not changing. Okay, but the kinetic energy is increasing. Okay, because you give the heat, right, to the balloon. So now it will move faster. Okay, the velocity of the speed of the molecule will increase. Okay, so means the kinetic energy also increase. So number 21, the answer is D, donkey. Okay, next one. Okay, so equal volumes of tea at 80 degrees Celsius are poured into the two containers of different materials. So diagram above shows the thermometer reading after 10 minutes. Okay. So after 10 minutes, you can see the temperature of the container X is higher compared to Y. Okay. So means the specific heat capacity of X is lower than Y. Okay. So the specific heat, the answer is B boy. Okay. Number 20 is B boy. Okay, next one, diagram 14 shows two metal cylinder X and Y in thermal equilibrium. So which statement correct about temperature X and Y? So thermal equilibrium, the temperature must be same for both objects. So the answer 19 is A. Okay, at 27 degrees Celsius, balloon is used in weather forecast that has a pressure of 100 kilopascal. So as the balloon reaches a certain altitude, the pressure decreases to 19 kilopascal. So what is the temperature at the altitude? So this one using the gas law. Okay, so pressure and temperature. So this one is a pressure law. Okay, so P1 equals to T1. Okay, to P2 divided by T2. Okay, so P1 is 100. Okay, 273 plus 27 is 300. Okay, so P2 is 90 kilopascal. Okay, and then divide by P2, you need to find. Okay, so number 24, you just cross multiply. Okay, to find the answer. So number 24, the answer is A, negative 3 degrees Celsius. Okay, 270 minus 273. Okay, this one you have to change back. Okay, I think you got 273 something and 270 Kelvin. Okay, and then you want to change back to degrees Celsius, you minus with 273. So that's why you get negative 3. Okay, so the answer before you change to degrees Celsius, the answer is 270. Okay, next question number, okay, the last one. Okay, before I stop. So diagram 16 shows the heating curve of 0.5 kg heated by 100 watt emission heater. So what is the specific heat capacity of the liquid? Okay, so this one since they give you the power, the PT is equals to MC theta. Okay, so the power here is 100. Okay, the time here is 7 minutes, change to seconds, 7 multiplied by 60, 420. And the mass here is 0.5. Okay, C you need to find. Theta is 70 minus 30. Okay, the increasing of the temperature. Okay, 7 minus 30, so you got 40. Okay, and then you just use the calculator. So number 21, C, the answer is C. Okay, 2100. Okay, so I think I stop first until here. Okay, so I see you on Monday for paper 2. Okay. If you have any question, you can just message me, right? Okay, thank you, class. Welcome.